All right, in this video, we're going to continue learning about antiderivatives. The basic idea for this video is we are going to continue using the power rule, which we learned in the previous video. That's this guy right here. But we're going to use it in some more challenging applications than where we saw it in the previous video. So I'm probably just going to end up doing a bunch of examples, maybe go through each one a little bit more quickly than I did in the previous example where we were just learning this stuff. So here's the first one. Suppose somebody asked you what the antiderivative of the function 3 over x squared were equal to. Note you could write that like this. If you could evaluate this, you're figuring out what the antiderivative is of this function right here. And I know this might be a little bit annoying, but the first thing I want to do is show you some things that you cannot do. It might be tempting to look at this and be like, the antiderivative of 3 is 3x, and the antiderivative of x squared is, let's see, x cubed, and then bring a 1/3 out in front. So I guess the antiderivative of this whole thing would be 3x divided by 1/3 x cubed. That does not work. And hopefully it won't surprise you too much that that does not work, because that same logic doesn't work in calculus 1. In Calc 1, when you're taking the derivative of a quotient, you have to apply this thing called the quotient rule. Maybe this looks familiar to you. You can't just take the derivative of the top and divide it by the derivative of the bottom. You have to do this weird f prime g minus g prime f divided by g squared thing. And you're like, you want me to do that? You want me to use the quotient rule here to figure out the antiderivative? Well, no, actually, because if you think about antiderivatives, what we're doing is we're going in the opposite order. So the quotient rule for Math 251 would only help us if I asked you to figure out the antiderivative of something that just so happened to look exactly like this. And if you're lucky enough to get something that looks exactly like this, well, then I guess its antiderivative would be f divided by g. But we don't have something that looks like this here. Right? We have 3 over x squared. So this quotient rule, while it's true, it's not going to help us in Calc 2 either. At this point, you're probably a little bit annoyed. You're like, hey, quit telling me what not to do. How about you tell me what you should do? Well, how about this? What if we did some algebraic manipulation? Right, that's going to be a key thing to do in this class. Often you'll be given something and you'll look at it and you'll be like, I don't know the antiderivative of that thing. And I'll be like, right, but how else can you write it? Can you rewrite this in a different way so it looks a little bit different so that it fits one of the rules you have? Well, we don't have a whole lot of rules right now. Really, the only rule we have is the power rule and how to deal with constants and sums. So is there any way to rewrite this so that we could apply the power rule? And the answer is yes. Right, if you have an x squared down in the denominator of a fraction, you can rewrite that as x to the negative 2 up in the numerator of that fraction. What I'm saying is 3 over x squared is the exact same as 3 times x to the negative 2 power. And this fits a nice, useful form to use the power rule on. You might be able to do all this in one step, but I'm going to do this in 2 steps. I'm first going to recognize that I have this constant 3 here. So I'm going to bring that out in front of the integral sign. And then I'm going to figure out what the antiderivative of x to the negative 2 power is. And be careful here. This is very, very easy to mess up. Go through these steps a little bit deliberately your first few times. The way I like to do these is first you stare at the exponent, the negative 2. You know, like, okay, the first thing I got to do is add 1 to that exponent. I know in Calc 1 you always subtracted 1 from that exponent. So in Calc 2 you're going to be adding 1 to that exponent. What's 1 more than negative 2? You're like, negative 3, of course. Nah. 1 more than negative 2 is not negative 3. 1 more than negative 2 is negative 1. This is going to be x to the negative 1 power. But then I'm not done here. Remember, when you're using this power rule, you always have to divide by whatever your exponent ends up being, or multiply by the reciprocal of that exponent if that's easier for you. So I have 1 divided by negative 1. Which looks really weird. You're like, wait, isn't 1 divided by negative 1 just equal to negative 1? Yeah, it is. I'm only writing it in this form so that you can kind of follow all the pieces. You can keep track of where everything goes. If you want to jump all the way down here and call this 3x to the negative 1 power, you should feel free. And I'm like, is that your final answer? And you're like, I think so. This is a pretty good answer. You leave your answer like this, I'm pretty happy. But remember, when we're taking antiderivatives, when we're taking integrals, we're really looking for a general antiderivative, a family of functions, so that when you take the derivative of that family, it gets you back to this 3 over x squared thing. So I guess we should tack on this plus c. You can leave your answer just like this. Some people think or say that your answer should be rewritten in the same format as your question whenever possible. So since this did not involve negative exponents, you might want to rewrite this as negative 3 divided by x plus c. Right, the negative 1 is x to the first power down in the denominator. But I think either way is totally fine. I don't see any real advantage to this form over this form. All right, here's another example. Suppose we were told that f double prime of x, the second derivative of some function x, is 10 over x squared plus 10x. And what you're asked to do is to find f of x. Not f prime of x, but f of x. This is 2 layers removed from here. We're going to have to take 2 different antiderivatives. And you're like, no big deal, I did that before, right? But when you did that before, here in our second example of the previous video, we were given some information that allowed us to figure out specific antiderivatives as opposed to general antiderivatives. We were able to solve for C and D. That information is not given in this problem, so I want to show you what to do in that case. And I think what else you'll see is weird things going to happen when we try to apply the power rule here. Because at first glance, you're like, oh, this is easy, man. I just did this over here. Why are you making me do these exact same things again? It's not the exact same, but it's pretty close. The 10x thing, yeah, I got that. And the 10 over x squared, you just showed me how to do that. Well, have faith, or have no faith, in that this problem is pretty hard, and it might be worth following it through. First step, let's find f prime of x. To find f prime of x, we want to take the antiderivative of 10 over x squared plus 10x, which you can write this way with the optional parentheses here and here. So the idea here is to find f prime of x 1 layer removed from here. We just take the antiderivative. Oh, right, I learned in the previous problem that it's beneficial to write this as 10x to the negative 2 power so that I can apply my product rule. I say product rule? Not the product rule, the power rule. Sorry, I misspoke there. And before applying my power rule, might want to split this up into 2 different integrals. And if you feel the need, you can pull the constants out in front as well. What I'm saying, perhaps 2 steps in one here. I can rewrite this as follows. Assuming that all makes sense, we can go through and we can actually use our power rule. So we'll leave the 10 alone for now. X to the negative 2 power. Well, we already saw that over here, but I'll go through it one more time. First, add 1 to the exponent. Be careful when you add 1 to negative 2, you get negative 1. And then divide by whatever that power ends up to be. You don't have to write it in this form if you want. If you prefer to jump down to here, we're good. I'm just trying to show the details for anyone who needs the help. And then in my next term here, I got this 10, and then I want the antiderivative of the x. Well, let's see, this x is x to the first power. If I add 1 to that exponent, I would get x to the second power, but then I'm not going to be done. I still have to multiply by the reciprocal of this exponent that this ends up being. And then don't forget to tack on your constant here. And 10 times 1/2 is just 5. Whoops. So I'm going to write plus 5x squared plus c. And so this is f prime of x, the derivative of the function of f of x that I'm looking for, the antiderivative of f double prime of x. That gets me to this step here. A couple of comments, things I haven't touched on. This antiderivative right here really should have a plus c at the end when I figure this out. And then this one should have a plus c as well. And you may have noticed that I didn't write a plus c and another plus c. I just wrote plus c at the end of the whole thing. How can I get away with that? Well, the idea is there's any constant you want here, or I guess right here, and there's also any constant you want here. But any constant plus any other constant is just a constant, right? Maybe you're thinking this one's a 7 and this one's a 42. Fine, but 7 plus 42 is just 49. I don't need to write plus c plus c. I can just write plus c once because the sum of 2 different constants is just a constant. And since these constants are arbitrary, I can get away with that kind of thing. So that takes me to this step. We're not done at this step, and you're like, all right, this is a step where you solve for c. Well, often it is, but not in this case. Because I didn't give you any information about f prime of x, we are not able to find a specific antiderivative of this function. We just have this general form of the antiderivative of this function. You're like, that's going to mess things all up. It's really not. Don't worry. I'll show you how. So our last step, to turn this into f of x, we'd say, well, f of x is the antiderivative of f prime of x. And f prime of x we just solved for. We got that it's negative 10x to the negative 1 power plus 5x squared plus c. So if we could figure out the antiderivative of this thing, we'd be in good shape. First step, same thing we've been doing. Well, we have a sum of 3 terms this time, so let's break that up into 3 different integrals. Okay, and some of them have constants out in front of a variable, in which case we should take the constant and pull it out in front of the sign. And yeah, you could do that in 2 steps if that's your thing, but I'm just going to do that in 1 step instead. And that takes me to this line. And you're like, yeah, I'm going to pause this video because I got it from here. You might not want to do that because something really tricky happens here. And what happened? The tricky part is with this term right here. It looks like you could apply the power rule, right? In fact, the way I wrote the power rule, you could apply it right now. You're like, this just says that x to any n right here, I just follow these steps. But look what happens if you try to follow those steps. If you try to follow those steps down here, you'd add 1 to the exponent, and that would get you a 0 here. And then you wouldn't be done. You're like, x to the 0 power, that's okay, I can deal with that. Okay, but keep going. You wouldn't be done. You'd have to divide by 0, multiply by the reciprocal of that 0. You get a 1 over 0 here. That's bad. Right? We can't divide by 0. 1 divided by 0 is undefined. There is actually a little caveat here that this new power rule doesn't always work. I didn't write it at the time because I wanted to save it for an example when we needed it, but it's true that this power rule only holds if n does not equal 1. And that kind of makes sense because if you look at this formula right here, if n equals -1, this is going to be bad. So it makes sense that this formula doesn't work. And so you're like, oh, we've done this before. You keep telling me what not to do. How about you go ahead and tell me what to do? Well, what to do is figure out what this was the answer for in Calc 1. You took a Calc 1 class and your teacher asked you to take the derivative of something and you were like, oh, I got that, teach. My answer is x to the -1 power. What was that question? And now you're like, damn, this is hard. Yeah, I learned a lot of stuff in Calc 1. I don't remember that off the bat. Okay, maybe I can give you a little hint. Maybe it had to do with logs. Maybe you remember from a Calc 1 class that the derivative of the natural log of x was 1 over x. Maybe that rings a bell when it's written in this format. But remember, 1 over x is just x to the -1 power. What I'm saying is the derivative of natural log of x is x to the -1. And therefore, the antiderivative of x to the -1 is the natural log of x. And you're like, oh, okay, so I write -10 natural log of x here. Yeah, almost. I'm going to return to that in just a sec. Let's go through the rest of these first. I have this 5. If I stare at this exponent, I want to add 1 to the exponent. That gets me x cubed, but then I'm not done. I have to multiply by the reciprocal of that 3. I have to multiply by a third here. And then for this last term, you're like, oh, this one's really hard. See, it's really not, right? You've done this before. Just instead of writing the letter C, there was a specific constant in there, 7. And I was like, you could use the power rule if you really want, but nobody ever does. What students instead do is memorize that when they have a constant, all you got to do is tack on the variable, x in this case. It's the same thing. Same thing that we're doing here. We have a constant. It's just that constant isn't specified. It's an arbitrary constant. All you're going to do is write it as cx. And then you're like, oh, and then I'm done? No, because we need another constant. But what do you mean we need another constant? There could be a plus 49 right here. And then when I took the derivative of this with the plus 49 at the end, it would get me right back to this. Right? Think about if there was a plus 49 here and you took the derivative. Can you see how it would get you back to this line right here? The idea is this has to be a general antiderivative, so I have to tack on an arbitrary constant at the end. Just like I put a plus c here, I have to tack on an arbitrary constant here. And here, be careful. You do not want to use the letter c. Any other letter is fine. Some books will subscript it, put like C0 and C1 or something. I just choose another letter. I choose the letter D. You do whatever you want. But the key thing here is you have to make the point that there's an arbitrary constant here, and there's an arbitrary constant times your variable, which is x in this case here. Wow, that's a lot. That's my final answer. Just about. One more weird thing that I want to show you. It has to do with restricted domains. So maybe you remember that the graph of the natural log of x kind of sort of looks like this. It has this approximate shape. The key thing that I want to point out is it's only defined for positive inputs, right? If somebody asks you what's the natural log of -5, they're asking you what's the height of the graph over here at -5. You're like, it doesn't have a height. Oh, right, it shouldn't have a height because the natural log of a negative number is undefined, as is the natural log of 0. So y equals natural log of x, its graph just looks like this. That's a little bit problematic because x to the -1 is something that's defined everywhere except for at 0. All right, its graph ends up looking a little bit more like this, but that's not super important. I can put any number I want into this function except for 0. 1 divided by -5 is perfectly defined. It's somewhere over here, -1/5. Right? So what's going on here is I am going from this blue function to this red function, right? When I'm taking antiderivatives, but the domains don't match up. The domain of the blue function includes all numbers except 0. The domain of the red function only includes positive numbers, and that's problematic. Fortunately, there's a nice easy fix. The graph of y equals the natural log of -x looks a lot like the graph of y equals the natural log of x. It's just reflected over the y-axis here. Right? It's almost the same. There's a lot of symmetry going on here. You can either get that by being like, well, if somebody asked me to put -5 into this function, they're asking me what's the natural log of the negative of -5. They're asking me for the natural log of 5. Well, the height of the natural log of 5 maybe 5 is right here in my picture, is going to tell me what comes out of this function when I put -5 into it, right? If -5 is right here in my picture. At any rate, we're going to take advantage of that symmetry here. That symmetry, the fact that these graphs are exact copies of each other, except for the green ones reflected over the y-axis, is going to tell me that the slopes are almost the same. The slope here at 5 and the slope at -5 are almost identical, right? The only difference is this one is positive and this one is negative. And that's true for any value. There's nothing special about 5 and -5. The slope at 2 is the exact same as the slope at -2, except that one is negative and one is positive. What I'm saying is, if this blue graph, this part of the blue graph, represents the slope of this red graph, this part of the blue graph represents the slope of this green graph. And so what I can do is, if I want an antiderivative for the entire blue graph, all I have to do is be like, well, it's kind of the green part and the red part. I just have to put these together into a single function. And there's a nice way to write the green graph and the red graph together as a single function. And it's like this: y equals the natural log of the absolute value of x, right? That makes the graph of this function is exactly what you see in red and green together. And now my domains match up. Now I have the same domain in blue as I do in red and green combined, represented by this function. What I'm saying, that's me trying to justify why in this class, every single time you're asked for the antiderivative of x to the -1 power, you're supposed to remember to put absolute value signs around the x here. You'll say it's the natural log of x, but you'll put absolute value signs around the x. In Calc 1, you don't have to do that. In Calc 1, you're asked for the derivative of natural log of x without the absolute value signs, and you put on x to the -1. And that's fine, because when you're asked for the derivative of natural log of x, the domain is already restricted. We're only talking about this right side here. So we don't even have to worry about the left side of the graph. But when we're talking about the antiderivative of the stuff in blue, we need an answer on both the right and the left side of the graph. And the way we get there is by putting absolute value signs in. Okay, confession. I took Calc 2 way back in the day, and I'm sure my teacher taught me something pretty damn similar to what I just said to you, and it made 0 sense to me. I didn't understand it at all. And look where I am, right? I got through this class just fine. It wasn't super important. I didn't need to know why. I just had to memorize that the antiderivative of x to the -1 power is not the natural log of x, it's the natural log of the absolute value of x. So maybe just remember that one. One last example, then we'll call this good. And you're like, call it good already. Stop this. Well, I think this one's short enough that I can fit it in this little box. And it'd be good to get this in. I think it fits better with the topics of this video than it will the next one. So allow me like 2 more minutes and I'll finish this up. What if you're asked to figure out the antiderivative of 1 over the cubed root of x? You're like, whoa, this is going to be super duper hard. Nah, you just do the same thing you've been doing. All you got to do is recognize that this can be rewritten as x to the -1/3 power. Right? The negative is why it's down in the denominator here, and the cubed root of x can be rewritten as x to the 1/3 power. If you remember those exponent rules, if you can change radical notation into exponent notation, then this problem becomes pretty easy. The antiderivative of x to the -1/3 power, well, the first thing I would do is add 1 to that exponent. What's 1 more than -1/3? Maybe you can talk yourself into that being 2/3. It is 2/3. But then I'm not done. I have to divide by this exponent. Maybe it's easier to think about, rather than dividing by 2/3, you're multiplying by the reciprocal of this exponent. So you're multiplying by 3/2. Stick that 3/2 down here, tack on your plus c if you can remember it, and you're done. Like, ooh, I don't feel good about that at all. It's not as bad as you think when you do a couple of these. And if you're not sure about this answer, if you're afraid you flipped one of these fractions in the wrong direction, just take the derivative of this. 2/3 comes down in front. That cancels out this coefficient. Subtract 1 from 2/3. You're left with -1/3. That -1/3 means 1 over the cubed root of x. And if your problem is, oh man, I couldn't get from here to here, well, don't worry. There's not that much algebraic manipulation we have to do. You have to recognize that denominator means negative exponent, informally speaking. And then roots, 3rd root, 4th root, 5th root, correspond with these fractional exponents. If this were the 5th root, it would be the 1/5 power. 2 minor things that you probably don't care about, but I caught them when I was watching these as kind of a proof. This first one, I never took this 5 times as 1/3. It just looks weird to me. I think it should be rewritten this way. And then second, I made an argument somewhere up here that some people think that the answer should be rewritten in the same format as the question, so no negative exponents here. I guess you could use that same logic to argue that I shouldn't leave this in exponent form. I should write it back in radical form. It's by no means wrong here. In fact, I'd go so far as to say it's totally fine, but maybe just personal preference. If you want, you could write this as the cube root of x squared as opposed to x to the 2/3 power.